Hello there. I'm going to work my way through the derivation here to find the E field over here at point P due to this entire rod's charge. So it's going to have charge capital Q, and you can tell from the direction of the E field over here at point P, which is away from the rod, through P away from the rod, that the total charge on this thing, which is Q, must be positive, since the field is emanating away from the charge distribution. If you have a collection of individual charges, you can use superposition for the E field, and you don't have to use the technique we're going to work through here, but for a region of space or an object that's been charged, so that it's instead of individual charges, it's a distribution of them, you're going to have to use some technique similar to what we're going to work through here. So a good place to start would be the E field, which is defined to be Coulomb's constant times the total charge divided by the distance squared away from the charge distribution times the unit vector. And this formula I've written down here, this expression, would work if you had one or two or three charges and you wanted to know the E field in a particular area due to those charges. You could calculate E for each of the charges individually and then add them up in a vector sense. And that resultant would be the E field at that point. But it won't work for this particular expression because this is a distribution of charges in a region of space where we can't do that simple task. Well, that doesn't actually sound all that simple. This using some calculus here is actually probably a little bit better. Some things we should note before we move on. Since this expression is a function in both Q and R, we need a way to eliminate one of those variables if we're going to be able to use straightforward calculus without having to use some multivariable calculus or something like that. So we'll have to come up with a way to do that here in a minute. And also, as R goes to 0, so as the point P where we're measuring the E field got closer and closer to the charged rod, this expression actually would break down. So we would have to move into the quantum mechanical range or something if we're talking about, an atom's width away from the charge distribution, so away from the charged rod. So what we've done here, you can tell that, or maybe it's not that easy to tell, but here at point P, that's actually the origin for the XY plane. So we've oriented the charged rod, which to simplify this, we're going to say that the charge distribution is even. So in this little area, it's dx right there. It'll have the same amount of charge as the same exact length of rod over here. And we've oriented along the x-axis, not at the origin, but separated from it by a distance a. Okay, and you'll notice how this is written. Calculus students will recognize the kind of notation here. We're going to define x to be the distance on the rod away from the y-axis, so away from the origin, and we're going to define dx to be some differential element here that contains some differential amount of charge. The length of the rod is L, and L and A are both constant, so the length of the rod is not going to change, and the point at which we're measuring the E field, which is a distance A away, that's not going to change either. Notice that a technique we're not using here, we're not talking about the E field everywhere in space, it's just literally at this one point, and we're using symmetry to simplify the explanation of how this is going to go down. When you learn about center of mass, one of the things you talk about is the linear lambda equals linear density, but in this case, instead of linear density being mass per unit length, it's Q divided by L. So the total charge, which is positive in this case, by the way, if I don't tell you what a particular charge is, the assumption is it's positive. So Q over L is the charge per unit length. So this little tiny region here, which is dx, contains charge dq. So you can see now we've actually related the total charge to the total length is a constant. Well, the differential charge per differential length is also that same constant, and we're going to use that to our advantage. So lambda times dx is going to be dq, which means it's time to now revisit our definition for E field. What I want to know is, from this little tiny chunk of the rod, length dx with charge dq, which is lambda times dx, by the way. I want to know what's the E field due to this one little piece way over here. And then what we're going to do is use calculus to, sum them all up. And we'll find out what the E field, the total E field from the entire distribution of charge along this rod, what it is over here at P. So let's rewrite this expression. The differential E field, and one of the things I want to mention here is we're not going to do this as a vector but a magnitude instead. We actually have been told here that the E field is out, or I could have told you that the charge is positive. So over here at point P, by doing this sort of analytically without having to do necessarily any math, we can see that the E field is going to have to be, or the direction of the E field is going to be that way if this is a positive charge, because E field lines always emanate from a positive charge, as opposed to negative where they would end up there as opposed to starting from there. So the differential E field from this little tiny dx equals k times dq divided by, instead of r now, we said that the distance from here to where that little differential element is located is x, so we can replace r squared with x squared. And we're not treating this as a vector, this is the magnitude quantity. So what I could do now is to replace dq with this differential trick we did up here so when you do a problem like this, you're looking for a way to get rid of one of the variables, and we're using this linear charge density thing. That's the technique for this particular kind of problem. So we're going to replace dq with k times lambda times dx over x squared. So now what we've got, here, let's rewrite dE over here. So now we've got the differential E field over here is equal to k times lambda times the differential x over x squared. And if we do that for all the values that x could be, for all the little regions, so there's a dx right here and another one right next to it, another one right next to it. If we do it for all of them, we should have the definition of the total E field. So the way to do that is to integrate both sides. So the integral of dE from 0 E field, meaning there's no charge we're dealing with, all the way up to the total E field of dE, that's actually a very simple integral. That's actually just E. So that's the E field that we're actually looking for. But then we have to integrate the other side. And k and lambda are both constants. So k times lambda, and then an integral, we'll do the limits here in a minute, dx over x squared. So this should be a straightforward power rule integration. That's x to the negative 2. Other things I would like to point out, since we're using, which is common in physics, since we're using limits here, these are definite integrals. I don't have to use the constant of integration, but I've got to get the limits right. That's the trick, though. So if we look back at our picture here, the closest point P is to the charge distribution, to the rod, is A. So that's point right there. The farthest it ever is A plus L. So way down here is point A plus L on the x-axis. This point right here is A on the x-axis. So the closest it ever is, the lower limit, is A, and the farthest it ever is, the upper limit, is A plus L. So now E is just going to be the integral of dx over x squared. And one of the things, this may be an extra step, but I don't know how much calculus an individual watching this has done. So you could simplify it slightly by actually making it x to the negative 2 dx. And now the fact that it's power rule, that's how you would solve this integral, kind of jumps right out, okay? So the integral of x to the negative 2 power, you add 1 to the exponent. Well, you multiply, you add 1 to the exponent first, and we get a negative 1, so I multiply my expression by that, and my expression is now x to the whatever this is plus 1. So in case you didn't follow that, E is going to be k times lambda times quantity, x squared integrated dx, the integral of x squared dx is negative 1 over x. So negative 1 over x. So the integral of x squared dx is negative 1 over x. And my limits are from a to a plus L. And I want to mention that in a minute here, we're going to want to get rid of this lambda, but it's okay right now. It's a constant and we could calculate it, but I'd like to have this in terms of the charge instead of lambda. So we'll revisit that in a minute. Let's actually do the algebra related to our limits first. So k times lambda, and then I've got, let's move actually the negative out in front right here. So we're going to take this negative and move it out to the front. So then I've got 1 over x, a to a plus L. So E is now negative k times lambda, and I've got 1 over a plus L minus 1 over a. So you plug in the top value here, minus plugging in the bottom value there, 1 over a plus L minus 1 over a. And I think the easiest way to write this guy, sorry, I'm making my lines a little thicker, is I'm going to do common denominator. I'm sure there's some other clever way somebody's come up with, but whatever, I'm going to do that, and my algebra should work out. Normally someone's watching me do this, or several someones, and they can tell me, oh, you've done this wrong. So let's pray this works out. So let's simplify this. E is negative. Oops, I messed up my k went crazy on me there. Negative k times lambda. And then if I find a common denominator, it's going to be a over a times a plus L minus this guy over a times a plus L. So a minus a plus L all over a times a plus L. Common denominator. So a minus a, of course, it goes away. End up with a negative L, and I've got a negative right there. So the a's drop out. So I got a negative L, this negative, and this negative here and that negative right there cancel each other out. I have positive L on top. So now I've got k times lambda times L over a times a plus L. Okay? And it's worth remembering right now, lambda equals the total charge on the rod divided by the rod's length. So I can plug that in up here. So E field is now k times total charge over length times length over a times a plus L. The lengths cancel each other out, and I actually get an answer that I can use. K times Q divided by, here, that I don't like the way that's going to bunch up right there. So I'll go right down to the end. E equals k times Q divided by a times a plus L. So a couple of things that are worth mentioning. If A, let's go back and look at our diagram. If A over here becomes very, very, very large compared to L. So you're like, instead of if the rod is 1 meter long and here we're maybe a few centimeters away, if instead A were like half a kilometer, maybe that's a little much, but 100 yards. If A is very, very large compared to L, then this expression, so for A much, much greater than L, this expression actually becomes approximately k times q over a squared. So it actually looks as if, so when A is really, really large compared to the length of the rod, instead of it being a rod, it looks like a point charge. So the charge is at a point A away from it. So we actually ended up with an expression and that's what we should see. For very large A, this thing should look like a point charge. So we ended up arriving where we needed to arrive. And for very small a, the function behaves very strangely. You could visit that in a lot of different ways, but we're actually going to leave it there. All right, there's one down.